take too long to talk about 3.4 parallel lines and perpendicular lines and how they relate with one another. We have three theorems, which are pretty straightforward, pretty simple. But we use the statements a lot, use the arguments a lot, so it's good to give them their own theorems. And then two definitions. First thing I want to talk about, I'm actually going to skip to slide 3 here and talk about some definitions first. Perpendicular lines, okay, two lines that form right angles, correct? Yeah. Something you've learned maybe, I don't know, 5th grade, 4th grade, okay? The symbol that we're going to use for perpendicular is this upside down capital T, okay? And we read that phrase as is perpendicular to, okay? And if we look at the statement here in the picture, we say that AB, that line, is perpendicular to CD, and CD is perpendicular to AB. What is nice about things that are perpendicular, if I have two lines or segments or rays or whatever, a segment and a ray, a line and a ray, whatever the objects are that are perpendicular, perpendicularity is it's symmetric. Okay, it's symmetric, meaning that I can say if AB is perpendicular to CD, you can read it in the other direction and say that means that CD is also perpendicular to AB. Is that okay? All right. We saw that with parallelism as well. Okay, if I have two lines, L and M, and they're parallel, we said L is parallel to M, but that also means that M is parallel to L. You can do the same thing with perpendicular lines. Okay, read it backwards and forwards. But perpendicular lines provide us right angles. Okay. Perpendicular bisector. Okay, there's two components to this, and if you know what those two components are to the vocabulary word, you should never forget then the statement that is created. It says a perpendicular bisector, perpendicular meaning right angles, correct? Okay. Bisect meaning cuts into parts. That's what the sector part means. You got sections or parts. What's the prefix bi mean? Two. And geometrically, whenever we see the word bisect, those two parts have to be what to one another? Equal. Have to be congruent. Okay. So a perpendicular bisector takes some segment. Okay. We're going to take that green segment there. Okay. That is my initial segment. A perpendicular bisector cuts it in half, creates two equal parts. Not GF. Let's call it. Let's put M right there. G to M. And then M to H are congruent segments, okay? But at the same time, it gives you a right angle there at M, okay? So there's two components. We've talked about bisectors, right? Okay, a bisector, let's say I had, this way, G, H there, and put M there, okay? Anything that went through M was a bisector. So I could call this line L here a bisector of GH. But once that line L becomes perpendicular over here, we can better classify it as a perpendicular bisector. Does that make sense? Okay. So you should know what bisectors are. We're just now adding that adjective of perpendicular to it because it's more information. That's going to become a very, very useful property. Definition. It's a very useful tool for everything we do in Chapter 4. Every time we see an isosceles triangle, we're going to go back to kind of dealing with that perpendicular bisector. Okay. There's a lot of things throughout the course that we're going to need that understanding for. Okay. Hopefully those two definitions are not kind of mind-bending. Okay. Might be mind-numbing, but not bending. All right, so we've got a theorem here that says if two lines are parallel to the same line, then they're parallel to each other. Give you a visual of what's going on here. All right, we have a black line. Okay, so this black line, if we go back to the theorem, it's the same line phrase that they're using in the theorem. Okay, so the black line is this here same line that they're talking about in the theorem. Okay, so we're saying if two lines are parallel to that one. Okay, so I'm going to first give you that line. Okay, agree that that's parallel? Okay, looks like it. If we come over here to the algebra, it gives the same slope, right? So those two lines are parallel. Okay, I'm going to say, that going back to just the black line, I'm going to put in this blue one. It's a different one than that red one, right? Is the blue one parallel to the black one? Yeah. Okay, going back to the slopes again, we got that idea. But now I'll take the black one out, put the red one back in. What's the argument you can make about the black or the blue and the red one? Parallel. They're parallel as well. And ultimately what's going on here is we got the transitive property of parallel lines. Okay? If G is parallel to F and F is parallel to H, then G is parallel to H as well. Okay? And that's what that last theorem says. If you've got a collection of lines that you know are all parallel, you can pick out any two of them, and any two of them are going to be parallel. Okay, pretty useful. You know, our coordinate system that we see up here on the board right now, the rectangular coordinates of the x-y axes, is a collection of a bunch of parallel lines, right, and perpendicular lines. Okay. Anybody ever been to New York City? Okay, you ever looked on Google Maps at New York City or seen pictures of New York City from the air? All the roads are what to one another?
They're intersecting.
Yeah, they're intersecting, but don't they kind of look like our grid here? Okay. Every road that is east and west in New York City is parallel to the other roads that are east and west. Any road that's north and south is going to be parallel to any other road that's north and south. They create basically a grid very similar to the XY axes inside New York City. And a lot of cities are planned that way. Okay. Some cities aren't. If you've ever been to like Washington D.C., Washington D.C. wasn't planned that way, but city planners will use these parallelism ideas quite often. The next theorem we'll talk about says if two lines are perpendicular to the same line, then they are parallel to each other. Two lines perpendicular to the same line. So again, I'm going to start off with just this line here. Okay, so that's my same line that the theorem talked about. Okay, and I'm going to create one line that's perpendicular to it. So the red line is perpendicular to it. Okay, I'm going to pick another line that is also perpendicular to it. Okay, so there I started off with the if part. If two lines are perpendicular to the same line, red one and blue one, both perpendicular to the same black line, what is the conclusion you can tell me about the red line compared to the blue line? They're parallel. Okay, and that's all that theorem said. But think about why. What do you notice about those two angles that are green? They're what types of angles? Corresponding, and they're both right angles, right? So corresponding angles are congruent. So what's that tell you about those two lines? Got to be parallel, right? So we could probably do without having that theorem, okay? But we use that theorem quite a bit, and that concept of corresponding angles and right angles and that kind of stuff to make these lines parallel. So it does garner its own theorem. Okay, so two lines that are perpendicular to the same line are parallel to one another. And the last one looks like this here. Okay, now I'm going to start with two parallels. So it's kind of like almost the converse of the last statement. I'm going to start with two lines that are parallel. The blue one and the orange one are parallel. Okay, and you can see over there, negative 0.2x is my slope for the blue one and the orange one. Okay, I'm going to force this transversal to be perpendicular to the blue one. Okay, so I'm going to start moving this point around and try to get that angle of 48.84 right now. I'm going to try to make that 90 degrees. And then I want to look at what the conclusion is about the angle up here. So if I start moving that around to get it to be 90, okay, so I had started off with two parallel lines. I forced my transversal to be perpendicular to one of them. What does it tell you about the other one? It's perpendicular to it as well, right? Okay, and that's all this additional theorem here says. Okay, slide 5. If a line is perpendicular to one of two parallel lines, then it's perpendicular to both. Okay, and think about why. Before I even put any markings in there, if I told you the blue and the orange one were parallel, that angle right there, where this 90 is, is corresponding to this angle here, right? So what does it have to be? It has to be 90 as well, okay? So it's not a far stretch from the things that we've talked about in the past with corresponding angles having to be congruent for parallel lines to develop these additional things, okay? But we talk about parallel lines and perpendicular lines so often that we like to do it without needing to talk about corresponding angles and maybe same side interior angles and stuff like that. So we develop these theorems that we know to be true, okay? There's an assignment in Math Excel with 3.4. I don't think it's going to be something that takes you a really long time to do. I am going to, or we will be going through the rest of these slides tomorrow. Probably do slides 6, 7, and 8 tomorrow, and then go on to 3.5. There will be a test on Friday. Okay, so throughout this week, we'll finish 3.4 and 3.5. We'll review a day, and then Friday will be your test over chapter 3. That'll be the last day of the 9 weeks. Okay. We will have a retake. It'll be early next week. It'll probably be Tuesday next week, so I can get those graded and then added to the report cards before they get submitted on Wednesday. Okay. So just kind of plan ahead for this week, next week a little bit. That's the plan. I'll send out a more detailed email about when that retake will be, whether it be Tuesday or Wednesday. Probably Tuesday. That's all I've got for you today.
Fine.